All right, so welcome back. So let's continue. It's very nice to see you guys again in a week. So last time, if you remember, I introduced the zinc device, so what it is and what it has. So if you remember, it's like a long time ago. I think I showed you this device, which you have already used it for your lab, right? So you now know what zinc is. And it actually has 3 different pieces in it. So processing system, programming logic, and PSPL interface. So the first component was processing system. Basically, it's a CPU. Okay, it actually runs the operating system and runs your software code, right? And also, you can communicate with like other hardware logic. Either it could be like a custom hardware logic written by yourself, or it could be other like hardwired logic as well. The second piece was this one, programmable logic. So if it actually has like bunch of CLBs, configurable logic block. So that is actually FPGA. So if you write Verilog code, you actually compile it and synthesize it, and you download your design. Then what it is it actually has a bunch of lookup tables, right? So if you have a lookup table, you can basically implement arbitrary combination of logic. And also, it also contains like several flip-flops. So by combining them, you can make FSM, finite state machine, right? So that's basically what it is. And you actually have like a sea of CLBs in our like FPGA. The third one, by the way, this one also has like a DSP logic, which can be can be used to build some like a custom like a combination logic, such as adders, and so on. Okay. And the last piece was the interconnect, right? So now we actually have like a processing system and programmable logic, PS and PL, and now we actually need to interconnect them to make a whole system. So and the last piece is like a third one, which more specifically is AXI interface. So that's the last piece, right? So by putting all these things together, we can actually build like a hardware plus software system, okay? And that's basically that's basically everything about this course. We build software, we build hardware, and putting them together to build like hardware plus software system. That's what we do in this course. Okay, that's what we covered last time. And I believe I need to cover the last part of this lecture, which is about goals and questions. Okay, so let's go over several questions in this course. So here is your goals and question. Of course, the goal of the course is understanding hardware to better design software, or vice versa. If you really want to become like a power programmer, you better understand hardware. And if you really want to become like a power hardware designer, if you really need to understand software. So it's like an yin and yang. You cannot really separate the two. So basically, it's like both sides of a coin in computer. And the basic questions were, how can your software communicate with the hardware, right? Because if you write software, you want to control the hardware blocks, right? So how they can communicate, hardware can communicate with software, or vice versa. I'm going to go over that in this lecture. And how can I design my own hardware function and make it communicate with my software code? It's the other way, right? You actually, let's say you wrote some like a Verilog code, like a logic, and then you compile it and put it in your FPGA. Sometimes you want to access like a main memory and so on, right? How this can be done? I'm going to go over this question as well. And more specific questions, what is the hardware system to run? Let me go over one by one. So let's start with more specific questions. The first question was, what is the hardware system to run my software code? Okay, let's say you wrote some C code and you compile it and run it, and the Zinc FPGA itself actually has ARM Cortex-A9 CPU, which is ARM core, and that like CPU can run operating system as well as your code. Okay, that's the answer. And the second question is, what are the components in the hardware system? There are like some fixed components like SD card I/O or USB or Ethernet. There are some like fixed function like I/Os, and also there are some like programmable logic. As I said, there are CLBs, right? FPGA basically. There are a bunch of lookup tables. You can actually program it to build your own, whatever functionality you want. Okay? The third question is, how are the hardware components connected? So, as I mentioned, we actually use what is called AXI bus. So I'm not going to cover that much about this thing. I'm not going to cover much of this in this lecture, but the next one I'm going to go over a lot of these things, the interconnection. Okay, so you can actually use either dedicated wires or bus. Okay, dedicated wire is kind of point-to-point connection. Let's say you have two blocks and they need to communicate with each other, and you could actually have like a dedicated wire. So this wire is solely used for communicating between these two devices. Okay, that's like a point or like a dedicated wire, or alternatively you could use a bus, right? Let's say you have like a bunch of wires and you attach a lot of blocks to it, and then it's basically shared by all these like blocks. Okay, so in this it requires some like arbitration, because sometimes multiple components, multiple blocks actually try to access the bus at the same time. Then you need to somehow arbitrate this request, right? So that kind of burst arbitration is required. So you could use like a dedicated wires or bus. So the next question is how do they communicate? These are like a logic blocks. I mean the hardware logic. How do they communicate with CPU when my code runs? Okay, I'm going to actually go a lot more details in the next stack of slides. But the high-level idea is from like a software to hardware. You can actually you can do what is called memory mapped I/O. Okay, for example, you can actually map like some of these like registers, like control register or status register, from this like I/O blocks to memory space. So if you actually execute like a load or store instruction, that actually gets translated to some like it's like a commands to the block and so on. Okay. So the basic idea is, memory access using pointer to registers or on-chip memory. That actually gets translated to some like commands or data transfer from like a software to hardware. So we're going to go over more details in like next lecture. Also in the other way, the hardware actually takes as input the contents of registers or onto memory and gives the output to the register or onto memory. So here's a very, very simple example. Let's say, this is our system here. So let's say this one is CPU, where your software runs. Okay, so this one is, block RAM. You know what is block RAM, right? There's some like on-chip memory, SRAM. So there's some like on-chip memory called BRAM, block RAM, and let's say there's some like custom like hardware block you actually wrote. In this specific example, let's say that was matrix vector multiplication custom IP. So then what you could do is you actually copy the input data from like external memory to this BRAM. Let's say you want to compute the multiplication of A and B. Let's say you want to compute some value A times B. Okay? Then the first thing you need to do, the CPU actually copies these two operands over to BRAM. Let's say it actually copies the value of A and value of B to this BRAM. So now we actually have value A is here and value B is here. So you first place this like operands here, right? And actually you trigger computation by store some like a command to the specific like memory location. Then actually gets translated into like maybe it's like a start signal. Okay? Then what this one does is actually it reads these two operands from BRAM, and it does the computation and write the value back to BRAM. Let's say the A times B is written somewhere here in BRAM, some other location. Let's say here. Then now this CPU can actually read back this like computed value from BRAM. Okay, this is basically like an offloading model. So CPU first copies data into the BRAM, and it triggers computation, and then this like a logic, like hardware logic, actually computes the multiplication, and then the result will be written back to BRAM, and that will be actually copied over to CPU register. Okay, that's basically sequence of steps to compute this thing. And the third question is, what hardware function do I design? Okay, so in this, for the time being, we're going to do like a matrix vector multiplication. Actually, this one is very relevant for today's computation application, because it's very widely used for like a deep learning, and it's like a neural nets. So neural nets is nothing but bunch of like a matrix multiply plus matrix spectrum multiply. So the hardware design consists of like a MAC, like a multiply and accumulate MAC units, memory, and bus and control logic. And MAC unit is implemented with DSP slice. If you remember, there was like specific like logic block or the DSP slice. It actually contains some adder and multipliers. So if you make use of it, you can very easily implement this like a MAC unit instead of using this like lookup table. Lookup table can be very inefficient, but if you use like a DSP logic, then this MAC can be very easily implementable. And the last question is, what is my software code working with a hardware function? So eventually, as I said, we're going to make a simple neural network that runs on this ARM CPU, and some of these things will be offloaded to the hardware logic. Okay, and software code sets the memory for your MAC unit. As I said, it actually copies the input operand to the VRAM on-chip memory, and then initiate this like a computation and receive the result back from this VRAM. Okay, that's what's going to happen. All right? Question? So we are done with this like lecture 5. Any questions about this thing? So the lecture, the material I covered? 다들 뭔가 좀 피로해 보이네. 뭔가 좀 학생들이. Everyone looks tired today somehow. Right. Okay, let's move on. There's no question. How is the lab, by the way? How is the lab going? 어떻게 되어 있어요? TA한테 물어봐야 되나? 중간고사 8주 차요. 8th week. I think this one is like a 6th week. 그죠? 2주밖에 안 남았네. 시간 정해야 되겠다는데. 날짜 정할까요? 오케이. Why not? 네. 그러면 날짜를 okay, let's fix the midterm date. It will be the week of 23rd. Okay, April 23rd. So the options are the class time, 24 or 26. It will last for 2 hours. Okay, so it's like a 3:30 to 5:30. Likely, yeah. So would it be okay to do this exam on Tuesday? 2시간. 네. 수업 있어요? 어떡하지? 끊어서 본다고? It's a context switch. Like you just context switch and just come back to. All right. Yeah. 없습니다. 네. No lab on in week 8. 네, 24일 없습니다. 네. 그래요? How many of you actually have class at 5 on Tuesday and Thursday? Okay, many. Then can you actually start early, like 3 p.m.? No? No? 아, 원래 랩 시간에? That's an idea. Yes. 원래 그 주에 없어요. 원래 랩. 목요일에 원래 랩 없다고 원래. 뭐를 수강하고? 뭘 수강? 원래 수학 시간에 수강하고. 뭐 생각해 볼게요. 진도 좀 보고. 네. Okay. Okay. So what about then Thursday evening, 7 p.m. 괜찮죠? No conflict, right? Hopefully. Anyone has conflict? On Thursday, 26th, right? April 26th, 7 p.m. on Thursday. This is our usual lab time, right? So hopefully there's no conflict. 7시부터 9시. 아니요, 수업 없는 건 아니에요. 네. 화목인데 한 번만 예, 원래 한 번 빠질 뻔했는데 어떡하지? 고민인데. 한번 봐가지고 조금 여유가 있으면 그냥 Q&A만 받든지 할게요. 여유가 있으면. Okay, so if you so we're gonna make an announcement. We need to check our progress first, and then how many weeks we're gonna have. All right. So the midterm is fixed. So we're gonna have the exam on Thursday, April 26th at 7 p.m. our usual lab time. Okay. There'll be no lab on in that week. So we're gonna only have the midterm. And this is like the classroom will be to be announced. We're going to announce the classroom where we're going to take the exam. 네. How many of you actually have 예비군? How many of you actually have 예비군 on that day? 근데 예비군이 있으면은 보통 낮에 끝나지 않아요? 그래요? 보통 5시 전에 끝나지 않나? 한 번 안 해봐서? 출석 체크만 하지 않아요? 요즘? 24일부터 26일이라고? 실례지만 무슨 과예요? 무슨 과 하시죠? 건축? 학과랑 상관없나? 공대, 자연대 뭐 이런 거. 그건 혹시 다음으로 미루고 이런 건 안 돼요? 만약 한 명이면, 그러니까 다른 사람들이 다 되는데 한 명이면 조금 그것 때문에 조정이 그렇고 한 번만 조정을 한번 시도해 보시고 만약에 문제가 되시면 뭐 다른 뭐 방법을 좀 강구해 볼게요. Anyone else? There's anyone else who has conflict? 양구까지 가야 돼? Okay, April 26th is the day. By the way, when is the drop deadline? 언제 드랍 데드라인이 언제죠? 다음 주 목요일? 그 전에 봐야 되는 거 아니야? Okay. All right. April 26th. So both our usual lecture and the lab materials will be also part of they will both covered in the midterm exam. So please, study both these lectures and labs. Okay. Okay. 됐죠? 나중에 다시 어떻게 되는지 얘기해 줘요. 네, 네. 그냥 아무 말 안 하면은 그냥 별 문제 없는 걸로 알게요. 그 TA 그분한테도 알려줘요. 네, 나중에 저한테 다시. Okay, so let's move on. So let's move on to the next part of the lecture. So we're gonna in this lecture we're gonna cover how the software can access hardware components and so on. Okay, so how your software code can access, and control and access some part of these hardware components. That's the next topic. So there are two things. By the way, sorry because I just uploaded this thing like an hour ago. So sorry for like being late in uploading this thing. So there are two things we're going to cover here. So the first thing we're going to cover is how your software can access or hardware components. More specifically, we're going to cover how your software can access VRAM, okay, block RAM. And second part is how the hardware components can access the main memory, right? Because you only have like one global like a memory, like a main memory, which can be shared by both like a processor and your custom hardware block. Okay, so they can actually communicate using the same hardware. So there are two. The second part is how these hardware components can access the main memory, and the last one will be overview of lab 6 and 7. Hopefully, I'm going to finish this one today because we actually have like 25 more minutes than usual. So here is a simplified view of embedded hardware, system hardware. So it actually consists of processor and like CPU and memory controller. So because to the memory controller, DRAMs or a bunch of DRAMs are attached, right? So you actually there are a bunch of like DRAM. So we have DRAM device. It's off chip. DRAM. These things are basically attached to this controller like this. And this one is global memory. As I said, this is global memory shared by both processing system and programmable logic. And peripherals. Peripherals include the SD card, Ethernet, or even like a CLB, like configurable logic blocks, and DRAM. All these things are peripherals. And there are two buses, being used. The first one is system bus, which actually primarily connect this CPU and memory. Okay, so as a result, this one is very high speed. This is high speed bus. Okay, and the second thing is peripheral. So peripheral is basically connecting all these I/O devices. They are like I/O, input/output devices. Okay, so peripheral bus actually connect this I/O, and there's like a bridge between the two. Okay, so through the bridge, actually one request actually can propagate to from peripheral bus to system bus or vice versa. This actually bridge actually connects these two. Then the question is why we separate these two buses? Why not just using one? Okay, any guess why you're gonna use it? By the way, this one is high speed bus and this one is low speed bus. Why we separate them? Question, any guess? 왜? 속도가 많이 달라서. 그렇겠죠? 네. 다른 이유가 없겠죠. 속도가 많이 다르기 때문인데. So actually, if you actually do that, the speed of these two buses are very different with each other. What can happen is, this is like a slow traffic can actually block this like a high speed like transaction. 그러니까 빨리 차가 나가야 되는데 앞에 X 차가 막고 있으면 안 되잖아요. 그러니까 되게 느린 트래픽 때문에 버스가 블락킹이 돼 있으면은 빠른 트랜잭션을 해야 되는 이런 블락이 될 수 있겠죠. So the problem is if one of these like module can actually block this like a slow bus because it can take a long time to process the request, then this like a high-speed request will be blocked for a long time, right? So to prevent that kind of like a blocking from happening, we actually separate this like a high-speed bus and like a low-speed bus, and then we connect them using bridge. Okay, that's kind of very typical like common design pattern. So basic mechanism we actually use to communicate between like a software and hardware is what is called memory mapped I/O. So from like a software perspective, this like we map these like registers and memory from this like a module into the memory space. Okay, so for example, so if you want to connect like this CPU with BRAM, like a block RAM, then we in terms of the hardware, we actually use AXI interconnect. Advanced like extensible interface. AXI, by the way, AXI is the industry standard like a bus protocol, like a bus standard, and it stands for advanced like extensible interface. So we're gonna go over more details about this thing next lecture. In CPU, in processing system, and AXI interconnect plus BRAM controller plus BRAM in programmable logic. So there are four like modules are involved. So how this software can access BRAM? Then actually we have like a processing system here, and we have BRAM here. So it actually, there are like four different modules involved for this like a software to access this like a BRAM, like a block RAM. In the mechanism, there are two options we can actually do. We can have to access this like a block memory. The option one is consider these hardware components as part of memory. Okay, let's say we have like a BRAM. Then what you could do is you map this like a block of memory to address space, a physical address space. Okay. Then now you can actually access this like a physical location as if you access this main memory, right? So this like a block memory is actually mapped to your memory space. You can actually use like a load and store instruction to access read and write this like a block RAM. So this is called, by the way, memory mapped I/O, which is the default mode of operation in our design. So now once you actually map this like a VRAM into your memory space, then load and store instructions can access this like memory directly. The second option is consider as a device. So let's say it could be like whenever you install like a new hardware, you sometimes need to install driver, right? So in that case, this device is recognized as an I/O device, input-output device. Instead of like a memory, part of the memory is now like I/O device. So in that case, you need to actually access it through device driver. Okay, so that's like option 2. But as I said, our default like option is like memory mapped I/O. Okay. So how we can we access VRAM from software? The quick answer is we can actually use this VRAM space into like a virtual address space using mmap system call. Okay. By the way, how many of you actually know mmap system call? Oh. OS 안 들었어요? 안 들었나? 어디서부터 설명을 해야 할지 모르겠군. Okay. So let's say then like what is virtual address and what is physical address, right? Address translation. So okay. Hopefully I assume you know what is virtual and what is physical address. So in this system, this VRAM is mapped to physical address between 40000000 through 400001FFFF in physical address. Okay. So for example, if you actually store some value to address 40000000 in physical address, then actually that means actually that triggers write to the block RAM. Okay. In contrast, if you actually execute like a load instruction to the same address, like a 40000000, then actually what happens is it leads the value from the block RAM in the beginning, the address 0 of the block RAM. Okay. So this VRAM is mapped to physical address, between this 40 something and 401FFF. And by the way, for reference, this off-chip DRAM is mapped to address 0000 through 3FFFF. So if you actually have like a physical address space like this, let's say you have physical address space. So the lowest like 1 gigabyte region, this one like from like 0000 through 3FFF. This like 1 gigabyte region is like a DRAM, mapped to DRAM, off-chip DRAM. Okay, and the next segment, next like 8 kilobyte region. So this memory space is mapped to VRAM, block RAM, on-chip memory. So if you actually do like execute like load and store, then actually you read and write to VRAM. Okay, this is like address mapping. So in general, like each like hardware component is assigned its own physical address. And let's say you have like a multiple peripherals. Let's say you have like VRAM, you could have like SD controller, you could have an Ethernet controller, USB controller, all these like devices, like peripherals. They actually occupy like a disjoint like address segment in physical address space. Okay, so actually by reading from and writing to that like a segment, you can actually control the behavior of this device. This is what's happening. This is like a memory mapped I/O. So VRAM region starts at address 400000, and the question is who actually does this assignment? Who determines which block actually which module is mapped to which like a physical address region? It's actually the designer, like a system designer. So if you're actually using like a Xilinx tool, then actually you can actually, as you see in this figure, you can specify this block RAM region, like a starting address and range and like a end address. So you can actually configure this thing. So actually you can not necessarily map to the 40000000. You can actually map to like a different region of address if you want. So you can actually control it using this like a Xilinx tool. So and then, but this one is like a physical address. Okay, so it's like a physical address space. But in order for you to access this thing from your CPU, you need to actually map it to the virtual address space, right? Because each like program actually has its own like a virtual address space. All the pointers are basically virtual address pointer, right? So what this mmap system call does is it actually can be used to create virtual to physical address mapping. Okay? So before you use this thing, you first need to map this like a VRAM like a segment into your own virtual address space. And this mmap system call actually does that. Okay? So for example, these two statements actually does this. Like the first statement actually open this like a dev mem. Dev mem is basically entire physical memory. It's abstraction for the entire physical memory as device abstraction. So once you open it, this dev mem means like the physical like address as device. So and then the second one actually you actually execute mmap. So if you execute mmap, basically you map this like a device like address space into your virtual address space. This mmap. So I'm going to explain more about these two lines. So here's a more detailed explanation of this thing. The first statement is like open. So open is the OS like a system call to open files or any like a device, right? So in this case, we actually open dev mem. Dev mem is actually the physical system's like a physical memory. Okay. So what actually you open it with a flag like a read write. So it means you can actually read from this like a device and write to this device. By the way, this device is the physical memory in this case. And then you now execute mmap, like an mmap system call, like memory map. So it actually creates a new mapping in your virtual address space of the calling process. And it actually takes like a bunch of like parameters, null size times size of int, like protection flags, and mapping like attributes, and plus like file descriptor and offset. So whatever it means. So what it does is the following. So here, it takes like a bunch of parameters. The basic idea was actually, map some like a physical address space to like this virtual address space. It creates virtual to physical mapping. So as I said, let's say we have like a physical address space like this. This is a physical address space. Then the lowest address like a DRAM. And the next segment is like a BRAM, as I said, right? And what we want is we want to create a mapping between virtual address space to physical address space. And then now what this mmap does is it actually creates mapping between these two segments. So now after executing mmap, now this is like a virtual address segment is actually mapped to this physical address. So if you access like this pointer value, you actually access this location in the physical address. Okay, that's what this mmap does. So here, there are a bunch of like parameters. The first parameter is the if you actually have like some like a preferred like a virtual address you want to start mapping, then actually you can optionally put some like a virtual address, but in this case it's null. Null means basically just return whatever virtual address you want, the OS like wants. And the next one is size of the mapping. So how many bytes we want to actually create a mapping for. And the next one is protection flags. So in this case, read and write. So you want to actually both like a read and write to the region. But sometimes you want to limit it to like a read only or write only and so on. And in this case, it's both like a readable and writable, this region. And map shared is it's basically if you write the value to this like a memory, it can be visible to the other processes as well. Okay. Then what is not shared is kind of private. You can also designate as private region. So if you designate as private region, what happens is what is called copy on write. So if you actually try to write it, then now it actually creates like a new copy. So it's kind of more details of copy on write will be covered in like operating system. I'm not going over more details. So it's basically this physical memory is shared by everybody. This is what this flag means. The next one is file descriptor. So in this case, this file descriptor is like a dev mem. The file descriptor for dev mem is basically it's got physical like memory space, and this one is the offset. The last one is the offset. As I said, this this is where you're gonna start this mapping from. So this is the length, size, this one is the length of the mapping. Size times size of int, that's the length of the mapping. And this is the starting position of the mapping in this like a device memory space, device address space. So, so this one actually refers to the offset from the file descriptor. So in this case, this is a file descriptor for physical memory. So that means now we want to start mapping from physical address 40000000, where this VRAM region actually starts. 이게 무슨 얘기인지 아시겠어요? emmap은 많이 쓰니까 랩에서도. So I'm gonna explain it again in Korean, the same thing. 그러니까 emmap이 하는 건 뭐냐면은 우리가 그 물리적인 그 주소 영역의 최하위 영역이 D램 영역이고 그다음에 그 위에가 이제 B램 영역인데 이 B램 영역을 가상 메모리 영역에다가 매핑을 해주는 거예요. 매핑을 해주는데 이 우리가 알다시피 이 B램의 영역이 4000000부터 40001FF까지 B램 영역이잖아요. 그러니까 여기에서 4000000으로 적어진 이유는 요 디바이스, 그러니까 요 디바이스라고 하는 건 지금 아까도 얘기했지만 피지컬 메모리가 디바이스죠. 여기서는 그 후라고 하는 디바이스가 피지컬 메모리라고 하는 디바이스에 4000, 그러니까 처음 시작 주소로부터 4000000에서 매핑을 시작해서 저 사이즈 타임스 사이즈 오브 인트만큼의 그 길이만큼의 매핑을 만들고 싶은데 그 매핑 만든 거를 버추얼 어드레스에다가 매핑을 한 다음에 그 포인터를 반납하는 뜻이에요. 그 시작하는 주소에. 그죠? So if you actually the mapping was successful, the starting address of this virtual address space will be given, will be returned to you. Okay? So this is the FPGA VRAM. So as a result of executing this mmap function call, if it was successful, then you're going to obtain the beginning address of this VRAM region in virtual address space. Okay? So once you actually get this pointer, then it's like a normal pointer. So you can actually use it to read the value from. But read the value from and write the value to this region. Okay? So this is the FPGA VRAM pointer. So for example, you can actually use it in this way. So it's more like for the for loop, and you actually write the value to this like a location, like FPGA plus VRAM I. By the way, this one is the same as this one, right? FPGA VRAM of I element. It's the same thing, right? So it's as if you actually write to this like a location in array, right? So you write the value to this like a memory location, which actually writes the value to VRAM, right? Because the mapping was created between the two. And then you can actually do printf, and then you actually read. In this case, now you read the value back from VRAM, right? Although we actually use the pointer, because now we actually create a mapping between this region and this region. If you actually read the value from like this, like a pointer, then actually you read the value from VRAM, block RAM, in the physical address space. Okay? 백문이 불여일견이고 백견이 불여일 코 코딩 한번 해보는 게 100번 보는 거고, 그죠? 백문이 불여일견이고 백견이 불여일 코입니다. 그래서 직접 해보시는 게 just do it, okay? Right. So that's basically how we create the mapping between this like a block RAM region to your virtual address space. After that, you can actually read and write whatever. You can basically freely read and write from and to the VRAM. So reading from hardware components actually require a bunch of steps, and step 1, step 2, and so on. And the step 1 is let's say you want to read some value from block RAM, then you actually need to execute this load instruction. Of course, step 0 is create a mapping, right? Step 0 is like doing mmap, like to create mapping between virtual address and physical address. That's step 0, and the next step is like a execute load, right? Load instruction. So, but actually, load instruction itself takes a lot of bunch of like steps. Okay, so it first does like a TLV access for virtual physical address translation, and also it does like a non-cacheable access by default. By the way, non-cacheable means it bypasses caches. So if you actually map certain like memory region to hardware device like VRAM, then you actually bypass the cache by default. Okay. That's what's happening. So from here, I'm going to explain what's going to happen when you execute load instruction. Okay? If you have taken computer architecture and OS, it will be probably a review for you because there's a page table, TLB, and stuff. There's a memory hierarchy actually consists of a main memory plus caches. Main memory actually has dynamic RAM or DRAM, off-chip DRAM, and caches are kind of internal, like an on-chip structure to hold the most frequently accessed data on chip, right? By exploring locality. So there are multiple levels of caches. L1 cache, it usually takes 1 or 2 clock cycles. It's relatively small. And usually we have separate like instruction cache and data cache. This is L1 cache, right? The processor. The L2 cache is a little bit larger, like it's somewhere between like 100 kilobytes to 1 mega. It's actually more than 1 megabyte, but some like a small number of megabytes. There's a typical like L2 cache size and usually shared IND, instruction data. And L3 cache, is actually larger but slower. Okay, it takes like a 50 clock cycle or so, but it can be much larger. And some like architectures actually adopt like EDRAM instead of using like SRAM. They actually use embedded like DRAM for higher like capacity, better capacity. So there are like a memory and storage address space looks like this. User process always use a pointer in virtual address space, right? In the virtual memory system, each process is given its own like address space, right? It's like a virtual address space, and there's like a physical address space is shared by everybody. There's like a page table actually translating, virtual address to physical address. Also, there's like a file system namespace. It's actually the name of file, a path, right? Like a user bin or like home/home, like user ID /hello.txt and so on. Like it's some like a namespace for the file system. And by like this page table, this virtual address is actually translated into physical address. And using this file system, this file system namespace is translated to the LBA, like a logical block address, right? Let's say you read some like a block from your file, then actually this file system actually translate this like this file system namespace into like a logical block address to access like a specific block in the disk, right? So that's actually done by the file system. And also like a logical block address is further down to be translated into physical like block address space using like a firmware like FTL. So there are a bunch of like a memory and storage address space and requires translation using like hardware and software. And the page table is used for virtual to physical address translation. Let's say you have your program. Basically, all the pointers are virtual address pointer, and then there's like a page table here. So like if you have a page table, this like a virtual like address gets translated into like a physical like address. This actually contains the mapping information between physical virtual address to physical address, and generally this physical like a page table is really large. So the input to the page table is the virtual like address, and the output is the physical address, right? So kind of big table structure, but it actually holds an entry, like this page table entries for all the pages in your virtual address space. But if you actually have like a one level, like a linear single level address space is really big, okay? Because usually your address space is really huge, like usually 48 bytes address space or more, like today's architecture. So it can be very large. So the technique here is we actually use like hierarchical page table instead of like using like a one level page table. By using hierarchical, like a level 1, level 2, level 3, and level 4, you can actually reduce this like a storage requirement a lot for the page table. Okay, so I'm going to explain more in like the next like few slides. So here, once you actually have this is the same code we have seen before. So once you open a new file. I mean, in this case, the file is the abstraction for physical memory. So once you open the file, this foo is the file descriptor for the entire file, entire physical memory. Okay. Then now you use this file descriptor to create a mapping between this like starting address 400000 to the virtual address space in your program's virtual address space. So once you actually execute it, if it's successful, now this FPGA VRAM actually points to the starting address of the VRAM in the virtual address space. Okay, that's what's happening. So here, now, let's say you have created this like a virtual address table, this is a virtual physical address mapping using mmap. Then this information is actually stored in page table. So this one is a page table. Okay, so for simplicity, let's assume we have like a linear, like one level, like a page table. Then let's say our like a VRAM segment actually occupies like one page, like this. Okay, then we actually create a mapping between this virtual address space to physical like memory space, like VRAM space. Okay, so and this page table actually has the information between the mapping information between virtual address to physical address here. So let's say we currently this page D is actually mapped to this like a VRAM area in physical address space. That's the assumption. Then this like entry, like the third entry will actually hold the information for the physical address for this specific page. So what will be stored in the page table, the more specifically? So here, so for this like a third page, like page 3 is actually the the page for FPGA VRAM. Then once you actually look up the corresponding entry in this page table, it will actually contain the starting address of the VRAM, which is 40000000. So this information will be actually stored here. And if you ever access a location in this page, then you first need to look up the page table. And once you look up the page table, you know that, oh, the starting address of this page is 4000 in the physical address space. You actually calculate the offset, so to access like a specific like a location in this page. For example, let's say in this page, it's like the VRAM area. Okay. But what happens is instead of actually storing all these like a 32-bit or 64-bit like a value, we actually only store PPN, like a physical page number, if you remember, right? Because if you break down the address, let's say virtual address is here, then this virtual address can be broken down into two pieces. This one is like a VPN, virtual page number, and page offset. And if after this address translation, we only exchange this part. This VPN will be translated to PPN, physical page number, and this page offset is basically remain the same, right? So in this like a page table, instead of like holding the entire like a physical address for this like a page, we only hold this PPN, physical page number, only part of it, not the rest, because this part is remain the same. It's not changed after the before and after this address translation, right? So in this case, we only hold like this PPN, physical page number, in this like a page table. So in this like a specific case, because this like a physical address is 40000000, by assuming like a 4 kilobyte page, meaning that each of these like a page is like a 4 kilobyte in size. So if you assume like a 4 kilobyte page, we actually drop this like a page offset takes like a 12 bits because like 4 kilobytes, right? So the 12 LSBs will be dropped here, and we only store the remaining like MSBs, which is 400000. That's a PPN, physical page number for this like physical address. So as I said, this like a page table actually only holds PPN instead of the entire physical address. Okay? 네. B램은 그 온칩에 있는 되게 작은 메모리고요. 온칩에 있는 SRAM 기반의 메모리고, D램은 오프칩에 있는 조금 느린 메모리예요. 그러니까 약간 성능의 차이가 있고 용량의 차이도 있죠. 근데 B램은 거의 되게 몇 사이클 안 걸리게 짧은 사이클 안에 그 액세스를 할 수 있는데, D램은 상당히 오래 걸려요. 한번 오프칩으로 나갔다 올라오면 한 뭐 수십 사이클, 수백 사이클 정도 걸려요. 근데 이거 테레비에 내가 안 나오네. 더 좋아, 근데. 사람은 안 나오고 칠판만 보이네요. 목소리만 들으면 됐지 뭐. 오케이. By the way, this is like we talk about page table, and page table is like a private to each process, meaning that each process has its own like a page table. So if you actually run like a multiple processes or multiple applications at the same time, then each process or application has its own page table, and then it can be huge, because now there are you can run like a tens or even hundreds of processes running at the same time. Then you can actually the space cost for this page table can be very large. Okay, so and this page table is kind of too big to be held in like cache. So usually you put this like a page table in main memory. Okay, these page tables are actually put into the main memory. So page table may require like 4 megabytes per process. Because if you store like a 32-bit address space, page table can require like a 4 megabytes per process, which is too big to be stored on CPU chip and thus stored in main memory. Okay, and size of CPU cache is typically like 1 to 10 megabytes, which is kind of a little bit too small to hold the whole things if you have like multiple processes at the same time. Okay, so in practice, this like this page table is actually put in this main like a physical memory as well. Both the data, actual data, and the table are placed in the same like a physical memory. So it's actually very inefficient. If you actually want to, let's say you want to access like some specific location in the memory, then what you have to do is you have to first actually go through address translation through page table, right? So whenever you access memory, it requires at least like 2 memory accesses, right? First one to access the page table. So only after you access this page table, now you know what is the physical address for this specific like memory location, and then now you actually go to that like a location. So in this scenario, every memory access actually takes at least 2 like a physical memory accesses, because the first one to access the page table, and second one is actual like a load or store. Okay. So this is very inefficient. So now try to reduce this cost of address translation. We introduce a special purpose cache called TLB, translation local site buffer. So here the idea is now you actually place a small like cache that actually holds the part of this page table entries. Okay, most frequently used page table entries are held in TLB. So this is TLB, and it's kind of page table cache, which means it only holds a subset of this like a page table on chip, so that you don't actually have to go to off chip to access the page table, and you only access this thing if it hits in the TLB. So here this one is the previous view of our memory system, but now we add TLB here. So if you add TLB, we place the TLB here and here, so that whenever you access the memory, you first access TLB to check whether the address translation is there. Then if it hits, then now you can immediately calculate the physical address for the memory location you're accessing. So using that information, you can go to the memory location. This saves a lot of inefficiency in the system. So this one is what TLB looks like. So TLB, instead of like going to the in-memory page table every memory access, now you actually go to the TLB first, and then if it hits there, then now you exactly know where your data is in the physical address space. Then you can actually go there directly. Okay. So this is like what TLB looks like. So once you actually have virtual address here, then you use this virtual VPN, virtual page number, as a key to access this like a TLB. And if it hits, then it directly returns this PPN, like a physical page number. And then you can simply replace this VPN with a PPN to obtain physical address, right? So now the translating this VA to PA is completed using TLB, if it hits, right? And if it does not hit, then actually you actually still have to go to the main like a page table in memory, right? So that's actually slower than this like TLB hit case. And when you access this TLB, it also check this like a protection. So protection means, let's say you try to access some, privileged page. Let's say there's some like information which is maintained by the operating system. Usual process cannot really access that like a privileged like pages, right? So that kind of user mode or kernel mode. So that like that's also protected. And also it may be like a read-only page or write-only page and so on. So if you actually try to write to a read-only page, then actually this one actually detects this like protection violation to actually trap the operating system. Then the operating system actually show off the error and just quit, right? And so on. So the point here is that this like a TLB does not only address translation but also protection checks. And as I said, I briefly mentioned that, but these flat like or linear page tables are expensive. So if you actually have a large memory space, like virtual address space, then the cost of this storage cost of this page table is proportional to the size of virtual address space, which is huge in today's like a 64-bit architecture. So also like if you have like 100 plus Cs, each requiring like a 4 megabyte page, like a page table, and the total like a page table size is 400 megabytes, which is pretty big, right? And then also this point is, only at any given time you only use like a small subset of this entire virtual address space, right? The rest of the pages are basically not used. So to prevent like this like a storage save some space overhead from these page tables, what you do is you actually use like a hierarchical page table. So hierarchical page table is you first access a level 1 page table, and then if the entry is not there, is invalid, that means this like a specific like a segment of pages are not allocated, it's not being used, right? Then you simply just return, and you first check this level 1 page table, and that actually points to the beginning of the level 2 page table, and then you access like a specific PTE from the like level 2 page table, and this one actually contains the PTE you're looking for. So in this way, you can save a lot of like a space from this page table, especially when the most of this virtual address space is not being used. Okay, so that's the idea of hierarchical page table. And practically, like today's like Intel architecture, like x86, your PC or like laptop, they actually use like a 48-bit like address space. So now they actually have like a 4-level like address space. So here, you break down this virtual address into 4 like segments, like a PML4. This is a page map level 4, and directory pointer, directory, and table. You actually break down this entire virtual address space into like 4 different segments, and this one is like a level 4, level 3, level 2, level 1. Okay, so you start with like a level 4. You first access this level 4 page table, and then this one actually points to the next level, level 3, the starting address of level 3 page table, which is, by the way, page directory pointer table. And this one also points to the beginning of the next level, which is like a page directory. And finally, this one actually points to the page table, and then this page table actually holds the PT for the specific like memory location. Okay, so that means if you actually have like a TLB miss, or like if you need to do some like a page table walk, you need to actually access like 4 different places like this. So you need to access like 4 different like places whenever you need to retrieve this PTE. You first access this level 4 page map level 4 table, and then you access like this page directory pointer table like level 3, and then you access level 2. Finally, you access level 1. Okay, and at that point now you actually retrieve this like a PTE. page table entry. So because all tables are stored in main memory, in the worst case, this is like 4 memory accesses are necessary to retrieve this like a PT, page table entry. Okay. So, but it takes like a longer time, longer latency, longer like steps, but it actually save the space. Because now, if you have like a huge, like 48 bit address space, it's like a, number of pages are really a lot. There are a lot of pages, right? And then you, at any given time, only like a very small subset of these like pages are actually being used. So, these like a leaf node only have like a very small number of PTs actually. And most of these things are actually filtered in the like upper level, page tables. And then, once you actually retrieve this PTE, now you cache like recently accessed PTs into the TLB. Okay? TLB actually holds like most recently used virtual to physical address mappings. Okay? Also, this part is actually stored in TLB, and these like things most recently used like page directory entries, like they are also stored in special cache called MMU cache. Okay, so because there's a lot of locality in memory access. If this entry is used, then it's likely that this entry will be reused in the near future. So now we actually store cache like also this like a blue like page directory entries in the MMU cache as well. So this red one is stored in TLB, and this like a page directory entries shown in blue will be actually stored in MMU cache. Still, they are also maintained on chip, on CPU chip. So after, to summarize, once you actually start execute a load instruction, it triggers a lot of like a series of steps. Okay, what it does is the first step is it translates like a virtual to physical address done by the TLB, if it actually hits into TLB. And after this translation is done, now you can actually access the remaining steps. You can go through this remaining step. In case of VRAM, it's non-cacheable, so we don't really check the cache. So we bypass the cache and then go directly, to the CPU bus, system bus, to access this like a VRAM. So far, what we covered is like a step 1. So what happens, if you actually execute a load instruction, is first translated into like a physical address, and in this specific case of accessing VRAM, we bypass the cache and then go directly to the system bus. And we're going to actually cover these steps 2 through 6 in the next lecture, when we actually talk about interconnect and bus. So that's what we only cover like a step 1 today. Any questions about what we covered so far? 갑자기 길어진 느낌? 사실은 1시간이 좀 짧은 느낌이었죠. Okay, so let's move on to part 2. So the second part is kind of the opposite. So how we can make these hardware components to access the main memory. So like from this like a custom hardware to main memory, shared main memory. The most specifically, we're going to cover the mechanism called IOMMU, what it does, why we need it. So why we need IOMMU? So IOMMU means like an input-output memory management unit. IO is the input-output, and MMU is memory management unit. So why need it? The point is each like hardware device requires its own virtual address space. That's the point. That's the point I want to make. Why is it so? So here, let's say we have like a CPU here. Like this is big core, like a Cortex A15. This is CPU, and this is GPU. And we have like some like a devices. This is like a hardware device. Maybe could be some like Mac unit or some whatever device you actually wrote. This display controller. They all like a shared resource. Then the point is these hardware devices actually require their own like virtual address space. So what is the reason? So what happens if hardware components use like a physical address instead of using like virtual address? What happens if they only use physical address? So if you use like a physical address, these like a block of memory are not relocatable, right? Meaning that there's no translation. So your request actually directly go to the physical memory. So actually the region of memory you are using is actually fixed at design time, right? For example, if you have like this one like a physical address space, then this region is actually reserved for MP3 player, MP3 like decoder, and maybe this one is like reserved for display controller. This one is reserved for modem. This one is like reserved for codec, video codec, and 3D graphics and so on. So if you only access like a physical memory, there's no flexibility. You can only use like a specific like a segment of a physical memory. It's a fixed at design time, right? So each hardware component needs a fixed region of the physical address, which is which cannot be changed during the runtime. It's very, very inflexible. Then what if you only use text messaging for now? Let's say you're only doing like text messaging. Then what is being activated is like display and modem. The other MP3 player, codec, 3D graphics, they're all like unnecessary. So these like memories are not used, right? But even so, you cannot really reuse this part of memory because it's actually reserved for the specific like block, right? So there are a lot of like waste in the main memory resource due to the fixed like physical address location. That's the problem. Then what we can do? So now we can introduce what's called IOMMU. So IOMMU is each like hardware components use its own like virtual address. And also they also require like a swapping mechanism. Like some of these like virtual like physical pages are swapped out to like disk, or they come back by demand and so on. So IOMMU does a virtual to physical address translation for hardware components, not only for CPU, but also for other like hardware components. So now let's say we have like 3 different hardware. Maybe this one's video codec. Maybe this one is like maybe MP3 player. Maybe this one is camera module, and so on. Then each like hardware module actually itself is like its own like address space. I mean, they actually have its own address space, so that they actually have page table, its own like they have their own like page tables like this, and then this page table actually translates this like a virtual address to physical address, in the same way as the CPU page table actually does. Okay. So once you actually use IOMMU, now the situation looks like this. Now you can dynamically allocate this like memory to physical memory to different like modules or CPU. So your application requires a lot of memory, then you can allocate more memory to the CPU, or you can actually dynamically shrink or expand this like memory region depending on the demands, right? So it actually increase the utilization of your memory resource. So IOMMU, the point of IOMMU is each device needs its own like a TLV for like virtual to physical address translation before accessing the main memory, and the physical memory is shared by both CPU and other hardware components. That's the point. So like modern like devices, today's like a modern computing system, they actually provide IOMMU so that these like devices other than CPU can also use like address translation, and also they can use this memory more efficiently. All right, so before we finish, let me just go over like lab 6 and 7, which will be done this week and next week, or a little bit. So this week's like a lab is about BRAM. Okay, so now what do? You will have to use mmap. Okay, what you're gonna do is basically you create this like mapping between like a BRAM, like a block RAM, and your software, like your program, so that you actually read the value, write the value to BRAM, and read the value from the BRAM. Okay, that's what you're gonna do this week. And this is the path. This is the access path from your CPU to BRAM. So let's say this one is CPU. This is CPU. Your program is running here, and this one is the general purpose AXI slave. The BRAM is actually attached to here. BRAM. Block RAM is attached to here. Then what's happening here is that your request actually will go through this. By the way, this is CPU. This is BRAM. So your actually requests go through like multiple modules, starting from like a processing element. I mean, this is like a processing system, like this PS. Now we move on to AXI interconnects. I mean, this you go through this like a master AXI, general purpose AXI, ports, and it's connected to AXI interconnect. So this AXI interconnect is kind of switch, like it's crossbar. So one input actually is connected to one of the output ports. So now in this case, this incoming like input is connected to this BRAM controller. So now this request will actually forward it to a BRAM controller, and eventually this BRAM controller will actually control the BRAM to read or write the value. Okay, so that's how your signal, your request actually, which path your request go through. So if you see in this like a hardware diagram, this is your CPU, and this is the BRAM controller. So now it actually go through like a bunch of like interconnects like this, and then eventually the request will be forwarded to this like a general purpose GP AXI slave, and the BRAM controller is actually attached to here. Okay, so your request will actually take this path. And there are like a bunch of like interconnect switches, like a central interconnect, master interconnect, slave interconnect, memory interconnect, OCM, on-chip memory. I'm going to explain more about this thing, more of these things in the next lecture. The next week, like lab 7, is about communication between hardware components. So what you're going to add to like this week's lab is we're going to add like custom components. We will ask you to write some valid code to build your own IP, like the logic, right? And then what you do is we're going to make this your logic and VRAM and CPU work together as a one system. Okay, so more specifically, what I'm going to ask you, you actually provide a value to this VRAM and write this like a matrix vector multiply like MAC unit, and then you also just send the control signal using like in software. Then this software actually read the value from this VRAM, and it process this like operands and generate the output, and then write back to the VRAM. And finally, this your program will read this result back from VRAM. So it's like offloading some computation to hardware logic. So here in lab 6, we did something like this. Now we actually add your own IP. It's your IP, your hardware. And then what we add here is that now we add one more like this. So not only our software access this VRAM, but also it access the IP, because we need to control the behavior of the IP, right? Start, and then also read some whether it's done or not. Ready. All these things will be communicated using like this AXI switch, and then eventually also this like the value will be read from this VRAM to IP, and also this IP will compute the result and write it back to the VRAM. Okay, so there are three-way communication from PS, like a CPU to my IP, and CPU to VRAM, and VRAM to my IP. There are three-way communication between modules. All right, it's about the same. I mean, same figure. The only difference is that now we actually have two like modules attached to this like a slave, because one is the VRAM, the other is your own IP, right? So now we actually have like a two path of communications. All right, so I think that's pretty much it. So I'm gonna next week. So we're gonna actually not next week. Like on Thursday, we're gonna cover more about this like a hard communication between hardware components, and also talk about like interconnects, like AXI bus and so on. All right, that's it. So any questions? If you have questions, feel free to ask. Otherwise, we are done.